The next topic is the difference between the conservative and the non-conservative forces. So here we just want to develop another type of the work energy theorem, okay, and then we can talk about the conservation of the energy here. So what is the conservative and the non-conservative force? So let's consider the non-conservative force first. Let me use the symbol as the F non, okay, for the non-conservative force. Okay, so I will give example of the non-conservative force to you first. For example, friction, a resistance, and some applied forces. For example, the pushing force or the pulling force. Okay, so now you can notice that for the friction and the air resistance, right, we don't have the potential energy for this type of the force. Okay, so that's gonna be the first thing that you need to know. No potential energy for the non-conservative force. And then the second thing is the work done by the non-conservative force depends on the path that the object moves. Okay, for example, if I have object here, okay, if I have the object here, let's say, okay, so let's say that this is the initial position of the object, right? The initial position, okay, and then the object just moved to this position. So let's say this can be the final position of the object. Okay, so now if the object just move to this part, right, just the straight line here, if you have some work done, so let's say by the friction, okay, if we have the object on the floor, okay, so we have the work done by the friction. Then if we just change the trajectory of the object, for example, if we change trajectory to this part or to this part, and etc. Okay, so it means that the work done by the friction on the object here will be different, because the work done by the non-conservative force, right, it just depends on the trajectory or the path that the object moves. Okay, so that's be the one thing that you should know, right? So then what happened to the work done by the non-conservative force? Okay, it's gonna change to some energy. For example, the object is gonna lose the energy to the light, to the heat, or to the sound, or whatever. Okay, or maybe the object can gain the energy as well. Okay, so the energy of the object will be greater. But then how about the non-conservative force? Example is the gravity, the resonant force of the spring, right? And then in the physics 2 we can learn about the electric and the magnetic force as well. Okay, so now you can see that this type of the force will have the potential energy. We know that the potential energy of the gravity equal to the mgy, the potential energy of the spring, right, just 1/2 kx square. And we also have the potential energy of the electric and the magnetic force as well. Okay, so what we can get from this one, right? Okay, let's go back first. We said that the work done by the result of the spring, right, Ws equal to what? Equal to negative of the change in the potential energy of the spring, right, which is equal to negative of the 1/2 kx2 square minus the 1/2 kx1 square. The x1 and the x2, right, is going to be the initial and the position of, the end of the spring. Okay, remember? Or if we look at the work done by the gravity, right, it's just equal to minus delta U, which is equal to minus of mgy2 minus the mgy1, where the y1 and the y2 are the position of the object related to the reference level. So in this case, if you notice from these two equations, right, you can see that the work done on the conservative force, it doesn't depend on the trajectory of the object. Okay, it's gonna depend on the initial and the final positions of the object only. For example, if we move object from this position to this position, and let's say that if we have only the gravity, okay, if we have only the gravity here, so the work done by the gravity, right, from this to this, okay, so we have the three trajectory here. The work done by this gravity must be the same. Okay, it must be the same, because the work done by the gravity just depends on the initial position and the final position only. Okay, so then in the general case, we can say that the work done by the conservative force, right, is going to be equal to negative of the delta U, or just equal to minus of the U2 minus the U1, okay, which is the final potential energy, and then minus the initial potential energy. So okay, so now we have the work done by the conservative force. So what happened to the energy, right? So when the potential energy of the object decreases or increases, so it means that it's gonna convert to the kinetic energy of the object. Okay, so in this case, it means that if you lose the potential energy, the potential energy that you lose will go to the kinetic energy. Okay, but then if you gain the potential energy, so it means that the kinetic energy of the object will be lost. So now you can see that we have the transfer, right, between the potential energy and the kinetic energy. Okay, so let me take note first. So you have the transfer between, okay, the kinetic and the potential energy, okay, of the system. Okay, of the system. So I said the system because in the system you may have more than one object, so that's why I just call the system here. But now for this non-conservative force, right, as I just mentioned before, right, we can see that the energy loss, right, the energy loss via, okay, for example, heat, what else, sound, light, okay, and etc. Okay, so we have some energy loss here, or maybe we can have the energy gains as well. Okay, we can have the energy gained where for example the any pushing force, right, any pushing force. So if you have a block, okay, if you have the block here, oops, if you have an object on the block, and then if you just push like this, so you have an object on the floor, okay, and if you try to push the object by some force, so then you can see that by pushing force, right, so then you can see that the object will gain some energy, but don't forget that this pushing force is not the conservative force, it is the non-conservative force. Okay, so it means that it doesn't have the potential energy anymore. Now we just want to find another version of the work energy theorem that can separate between the conservative force and the non-conservative force, right? So let's just start from this one. We said that the work energy theorem, right, is the work done by the net force or the work done by the resultant force equal to the change in the kinetic energy of the system. Then again, in a system, right, if we have both conservative and the non-conservative exerting on the system, in this case we can say that we can just write down the work done by the resultant force, right, to be equal to the work done by the conservative force, and then plus the work done by the non-conservative force, okay, equal to the K2 minus the K1. But then again, right, we said that the work done by conservative force equal to minus of the U2 minus the U1. So here we have minus the U2 minus the U1, right, and then plus the work done by the non-conservative force equal to the K2 minus the K1. All then you can get that, okay, if you move this to the right hand side and if you combine K2 with the U2 and the K1 with the U1, right, you will get that the work done by the non-conservative force equal to the K2 plus the U2, okay, this is the first group, and then minus the K1 plus the U1, this is the second group. So now let's define the total mechanical energy of a system. Okay, again, so right here I'm using the word system. It means that in a system you can have more than one object. Okay, you can have 2, 3, 4, 5 etc. objects in the system. So let me define the total mechanical energy of the system to be the E equal to the kinetic energy and then plus the potential energy. Okay, the E equal to the kinetic energy plus the potential energy. Then in this case, this is going to be equal to the E2, right? This one is equal to the E2, the final total mechanical energy, and this one is just equal to the E1, the initial total mechanical energy. So in this case, you will get that the work done by the non-conservative force, right, is going to be equal to delta E, which is equal to the E2 minus the E1. Okay, so let's call the work done by the non-conservative force, right, equal to the change in the total mechanical energy of the system. Okay. Okay, so let's consider. So now let's consider a system, okay, without any non-conservative forces. Okay, so let's consider a system without any non-conservative forces. It means that we don't have the anti-resistance, we don't have any friction, and we don't have any pushing or the pulling force on the system. Then it means that the work done by the non-conservative force, right, must be equal to the 0. Okay, so then if this one equal to 0, it means that the E1 must be equal to the E2, right? The E1 must be equal to the E2. The E1 must be equal to the E2. On the other hand, we can say that the K1 plus the U1, right, equal to the K2 and then plus the U2. Okay, so this one called the conservation of the total mechanical energy. Or just simply say that the conservation of the energy. So in this question, it means that the kinetic energy, right, of the system can be transferred to the potential energy, or the potential energy can be transferred to the kinetic energy as well. So that's going to be the meaning of this equation. Okay, so now let's look at these examples. Okay, for this example, the two blocks are fastened with a light string passing a massive frictionless pulley, right? So we have the block MA and the block MB. So both are connected by the light string, okay, passing this pulley here. The block MA is on the rough surface, so this is the rough surface. Okay, maybe I can just make the dot here. Oops. To show that this is the rough surface. Okay, and connected to the spring of the constant K. So we have the spring with the spring constants equal to the K. Both blocks are released from the rest. Okay, so initially both of them are at rest, right? So we have the speed equal to the 0 meter per second, both of them. Okay, when the block MA actually stays at the spring equilibrium position, so this is at the equilibrium position. Okay, equilibrium. The block MB displaced by the h before stopping, right? So in this case, it means that the block MB here will be displaced by this distance. Okay, displaced by this distance. Okay, before stopping, so it's going to be displaced by the distance equal to what? Equal to equal to h, right, as it says, equal to the h before stopping. So again, this is the 0 meter per second. So now if the block MB, right, displaced by the distance equal to the h, it means that the block MA is going to be displaced by the displacement equal to the h as well. Okay, so it's going to go to something like this. Okay, to something like this. Okay, so now you can see that this displacement, right, is going to be equal to h as well. And then it's going to stop here as well at the 0 meter per second. So we just want to find what? Okay, now for the part A, we just want to calculate the coefficient of the kinetic friction, right? The mu between the block A and then the surface. Okay, the block A and the surface. Okay, so let's use this equation to solve this problem, because in this system we have the friction, right? And the friction is the non-constitutive force. It means that we're gonna have the work done by the non-constitutive force as well. Okay, so let's define this position to be the initial position. Okay, and then let's define here to be the final position. Okay, so we have the initial and the final position here, right? This is the initial position, and then here is with the final position. So we said that we just want to find the equation of the kinetic friction, right? The mu is related to the friction, and the friction is related to the non-conservative force. Okay, so we need to use this equation to solve because we have the non-conservative force here. Okay, let's just write down equation first. We say that the work done by the non-conservative force, right, equal to what? Equal to E2 minus the E1. But now we can say that the E2 just equal to the K2 plus the U2, and then minus the E1, right? The E1 just equal to the K1 plus the U1. Okay. Yeah. Let me just write down here. Okay. So now we just want to try for every all these variables, right? And sub it in and just solve the equation. Okay, one thing. At the initial and the final position, the speed of the two blocks equal to the 0. So in this case, it means that the K1 must be equal to the K2, which is equal to the 0. Okay. Now, if we consider the block MA, right, you can see that. Okay, so let's consider the gravitational potential energy first. Okay, the potential energy due to the gravity. If you consider the block MA, you can see that it will have, okay, the initial position and the final position, right, are just at the same level. So it means that the gravitational potential energy of the block MA doesn't change. But what's going to change is the elastic potential energy, because the MA is connected to the spring, right? It's just connected to the spring. So then if the block MA move to the right hand side, the spring will be extend. Okay, so it means that the block it will have the potential energy of the spring here. So then you can see that the U1 of the block A, right, is equal to the 0. But then the U2 of the block A, the final potential energy, okay, equal to the 1/2 K and then times the H square, because the H is the extension of the spring, right? Now, if we consider the block MB, okay, the MB doesn't connect to the spring, so it means that it doesn't have the elastic potential energy. But now you can see that the MB, right, just move in the downward direction with the displacement equal to the H. So now let's say that, okay, if we define the reference level to be maybe this one, okay, if we define the reference level to be this one, okay, so this will be the reference level for the block MB, right, for the block MB. So now, okay, at the initial position, the MB is at the reference level, so it means that the gravitational potential energy must be equal to 0, right? So we have the U1B, okay, must be equal to 0. But then how about the final potential energy? Okay, so in this case by the H, and now this position is below the reference level, so it's gonna have the potential energy to be the minus the MB times the G and then times the H. Okay, so then if we combine the initial potential energy together, we get that the U1, right, equal to the U1A plus the U1B must be equal to the 0 as well. But now for the U2, okay, equal to the U2A plus the U2B equal to the 1/2 KH square minus the MB times the G and then times the H. So that's going to be the initials and the final potential of the system. Okay, so we have this one, this one, this one, and this one already. So now let's try to find the work done by the non-conservative force, right? The work done by the non-conservative force equal to what? Okay, so we have the friction. The friction is opposed the motion, right? It means that the work done by the friction must be negative. Okay, it must be negative, right? And then the force Fk, and then times the displacement, which is equal to the h, okay, equal to minus. Okay, so now for the Fk equal to the mu, and then times the normal force of the block MA, right? Normal force of the block MA equal to what? Equal to the MA times the G. Remember, we have seen this many times already, right? And then times the H. So this is going to be the work done by the non-conservative force, which is equal to the work done by the kinetic friction. Okay, so now let's just combine everything into this equation. We have that minus mu, okay, times the MA, G, and the H, right, equal to. So now the K2 equal to the 0 plus the U2, right? The U2 equal to this one, equal to the 1/2 K and the H square minus the MB times the G and then times the H. Okay, this is the for the K2 and the U2 minus the K1 and the U1, right? K1 equal to the 0 and the U1 equal to 0 as well. So we have the 0 plus 0 here. So we have the H for each term, right? So the H can just cancel out, and then finally we can just solve for the U. Then we can get that the U, right, is gonna be equal to the MB times the G, and then minus the KH over 2, and then over the MA times the G, right? Okay, yeah, that's correct. Yes, correct, right? So this will be the answers. Okay, so now for the part B, we just want to determine a displacement such that both blocks will have the maximum speed. Okay, and you just want to find the speed as well. Let me use the previous figures again. Maybe just use this one. And reduce the size. Okay, look nice. So now let's say that, okay, we just want to determine the maximum displacement, right, such that both blocks will have the maximum speed, and we just want to find the speed. So how can we find the maximum value of a function? We need to find the derivative, right? We need to find the derivative of that function and just make it equal to the 0, and then we can solve that position, remember? So in this case, let's say that if the displacement equal to the x, okay, if the displacement equal to the x in both cases here, in both Mn and Mb, then we can say that the speed of the block here must be equal to the v depending on the x. okay, the speed of the block equal to the v depending on the x here, right? So now we can just do the same thing as we have done so far, okay? But one thing, the thing that's going to be different is the k2, right? The k2 is not equal to the 0 anymore, right? Because I mean right now we just want to find the kinetic energy of the displacement equal to the x here. So we can say that the k2 equal to what? Equal to the 1/2, okay, because both of them we have the same speed, right? Then we can combine them as the m1 plus the m2 and then times the v square. So don't forget that this v just depends on the position x. So what else gonna change? The u1, right? u1 just still to be the 0, so that's nothing changed. But now for the u2, okay, we need to change from the h to be the x. Okay, we need to change from the h to be the x. We get that the u2 equal to the 1/2 k and then x square, right? And then minus mb times the g and then times the x, okay? And the k1 equal to the u1 equal to the 0. Just take the note here. And one thing that changed is the work done by the non-constitutive force, right? So this one is going to be equal to minus the mu times the ma times the g and then times the x. So we just change from the h to be the x, and that's it. Okay, and that's it. So let's use this equation to solve. Okay, let's use this equation. We said that the work done by the non-constitutive force, right, minus the mu ma times the g and then times the x equal to what? Equal to the k2 plus the u2. Okay, k2 plus the u2 okay, and then minus the k1 plus the u1, but this one equal to the 0, we can just ignore it. Okay, so now we just want to solve for the v, right? We just want to find the v as a function of the x. So this is just simple. You can just move this one, right, to the left hand side and then combine these two terms together, and you just move this one to the left hand side as well. Okay, so then finally we can get that the v square, right, which is depends on the x, is equal to the 2 and then over the m1 plus the m2, which is coming from this term. Okay, and then the mb, right, minus the mu times the ma and then times the g times the x minus 1/2 k x square, and that's it. That's going to be the v square. Okay, but now this question needs us to find the v max, right, the maximum speed. Okay, so how? Okay, so to find the v max, right, to find the v max, okay, it means that the dv x by dx must be equal to what? Must be equal to the 0, right? So you have learned this one already. Okay, to find the extreme value of the function, so you need to take derivative of that function relative to the argument, right, and just make it equal to the 0. Okay, then how can we find the dv by dx, right? Let's use this. We know that the expression equal to dv by dt. Okay, expression equal to the dv by dt, or just equal to the v dv by dx, right? or just equal to the 0. Okay, or just equal to 0. So this term equal to 0. But now we have the v square, and we don't want to make the square root here, right? Because it's be too lengthy. Okay, we can just simply do something like this. We can say that, okay, derivative of the v square by dx, right, it must be equal to the 2 times the v, and then dv by dx, right? Derivative of the v square must be equal to the 2v dv by dx. Okay, so this term is going to be equal to the 0, because we said that dv by dx here, right, must be equal to 0. Actually, should be this type the x. Oops. Okay, now let's see. So it means that we just find derivative of this one, right, and make it to be equal to 0, and that's it. So here we can get that the 0 equal to, okay, derivative of this one, right? So we have the constant, the 2 over the m1 plus the m2. This is still be the same. And then we have, okay, derivative of this term, right, just equal to this value, equal to the mb minus the mu times the ma, right, and then times the t. Okay, and then minus, so now derivative of this equal to k times the x, and that's it. So then in this case you can conclude that, okay, the maximum speed occurs when the x equal to what? Okay, so now if this term equal to 0, right, it means that these terms must be equal to the 0 as well, right? Then you will get that the x must be equal to the mb minus the mu times the ma, and then total with the t, and then over the k, and that's it. Okay, this is going to be the position where we get the maximum speed of the two blocks. But now the question is, okay, so we get this one already, right? But now we just want to find this speed, so we need to plug in this x into this equation. Okay, but I mean it's too lengthy. I will just conclude for you. So after put this x, put the x above into v square equation, right, and do some algebras. Okay, and do some algebras. Okay, one gets the Vmax equal to the m2 minus the mu times the m1, and then times the g, and then over the k m1 plus m2, and then just do the square root. Okay, so these are the answers for these questions.